Hello there, and welcome to Worlds Beyond Seen. I'm so glad you found your way here tonight. Before we begin our journey into the deepest darkness of our planet, I'd love to know where in the world you're listening from right now. Are you tucked into bed, watching the ceiling? Are you curled up on a couch as the day winds down? Maybe you're somewhere in between wakefulness and dreams, and that's exactly where this story wants to meet you. Before we descend into the abyss together, I have a small invitation for you. If you enjoy these slow journeys through science and wonder, if you find comfort in learning while you drift towards sleep, I'd be grateful if you'd tap the like button and subscribe to the channel. It truly helps more curious minds find their way to these stories, and it means the world to me. But no pressure, of course. Just know that you're welcome here, always. Now, settle in, get comfortable, let your breathing slow, because tonight, we're going somewhere most people will never see. We're going to descend through miles of dark ocean water, past the realm where sunlight fades, past the twilight zone where the last glimmers disappear, all the way down to the ocean floor. Not just any ocean floor, but to a place where the Earth itself is being born. A place where mountains taller than the Himalayas snake around the entire planet like the seams on a baseball. A place where the very crust of our world splits apart and magma rises from below, where water heated to hundreds of degrees erupts from chimney-like structures, and where life, somehow, impossibly, thrives in complete and utter darkness. This is the mid-ocean ridge system, and what lives there, in that crushing pressure and eternal night, is more alien and wonderful than anything you've ever imagined. The hidden mountain range. Imagine, for just a moment, that you could drain all the water from the world's oceans. Every drop, every wave, every current, all of it suddenly gone. What would you see? You might expect a vast, flat plain of mud and sediment, a featureless desert of former seabed, but you would be wrong, spectacularly, beautifully wrong, because what you would discover, stretching across the entire planet like a vast surgical scar, is the most magnificent mountain range Earth has ever produced. A continuous chain of underwater peaks and valleys, rifts and ridges, volcanic mountains and deep chasms that wraps around the globe for over 65,000 kilometers. That's approximately 40,000 miles, if you're keeping track. To put that in perspective, you could circle the Earth at the equator 1.5 times and still have not covered the full length of this single, interconnected mountain system. This is the mid-ocean ridge, and it exists in every ocean on our planet. There's the Mid-Atlantic Ridge, running like a backbone down the center of the Atlantic Ocean. The East Pacific Rise, spreading at remarkable speeds beneath the Pacific. The Southwest Indian Ridge, the Southeast Indian Ridge, the Central Indian Ridge, the Gackle Ridge hidden beneath the Arctic ice. All of them connected, all of them part of this single planetary scale feature. And yet, until remarkably recently, we had no idea it was there. The story of its discovery is worth telling, if only because it reminds us how little we truly know about our own world. During World War II, as ships and submarines prowled the oceans, better sonar technology was being developed. Sound waves were sent down into the depths, bouncing off the seafloor and returning with echoes that could be measured. When the war ended, scientists began using this technology not for hunting submarines, but for mapping the ocean floor itself. In the 1940s and 50s, a ship called the Weimar, operated by Columbia University's Lamont Doherty Earth Observatory, crisscrossed the Atlantic Ocean. Day after day, it recorded echo-sounder data, measuring the depth of the water column. Back in the lab, a remarkable woman named Marie Tharp began plotting this data onto maps. What she saw astounded her. Running down the middle of the Atlantic, there was an enormous mountain range with a deep rift valley at its crest. She showed her findings to Bruce Heason, her colleague, who initially dismissed the idea. It seemed too extraordinary, too neat, too much like science fiction. But the data didn't lie. As more surveys were conducted, the evidence became irrefutable. There was indeed a massive underwater mountain range bisecting the Atlantic Ocean. They called it the Mid-Atlantic Ridge. And then came an even more startling realization. Similar features were being discovered in the Pacific, in the Indian Ocean, in every major ocean basin. The mid-ocean ridge wasn't a feature specific to one ocean. It was a global system, a planetary feature so large it dwarfed anything on land. Consider this. The longest mountain range on land is generally considered to be the Andes, stretching about 7,000 kilometers along the western coast of South America. The Himalayas, home to the world's tallest peaks, extend for about 2,400 kilometers. But the mid-ocean ridge system is nearly 65,000 kilometers long. It makes every mountain range on land look like a small hill by comparison. And it's not just long, it's tall. In many places, the ridge rises 2,000 meters, over 6,000 feet, above the surrounding seafloor. Some of its peaks break the surface to form volcanic islands. Iceland, sitting astride the mid-Atlantic ridge, is perhaps the most famous example. The island exists because volcanic activity along the ridge has built mountains so tall they emerge above the waves. The Azores, Ascension Island, Tristan da Cunha, all of them are peaks of the mid-ocean ridge, breaking through to the sunlit world above. But most of this vast range remains hidden. The typical depth to the top of the ridge is about 2,600 meters, or roughly 8,500 feet. That's deep, very deep. Deep enough that the pressure would crush most human technology. Deep enough that sunlight, even in the clearest water, never reaches. Deep enough that for most of human history, we had no idea it was there. The ridge is not a smooth, gentle rise. It's rugged, fractured, dramatic. The crest of the ridge is often marked by a rift valley, a deep crack that runs along its length. This valley can be 10 to 20 kilometers wide and up to a few kilometers deep. It's a wound in the Earth's crust, a place where the planet is literally pulling itself apart. Along this rift, volcanic structures rise. Seamounts, volcanic cones, pillow lavas frozen in strange, bulbous shapes. Fault scarps drop away into darkness. Hydrothermal chimneys belch superheated water into the cold abyss. The morphology of the ridge varies dramatically depending on how fast the seafloor is spreading. Slow-spreading ridges, like the Mid-Atlantic Ridge where plates separate at less than 40 millimeters per year, about 1.5 inches, tend to be rougher. They have deep rift valleys, steep slopes, and frequent faulting and earthquakes. The volcanic activity is more sporadic, more explosive, fast-spreading ridges, like the East Pacific Rise, where plates can separate at 150 millimeters per year, about 6 inches, have a very different character. They're smoother, with gentler slopes and more continuous volcanic activity. Instead of a deep rift valley, they often have a subtle axial high, a slightly raised area along the spreading center. The difference comes down to magma supply. Fast-spreading ridges have more molten rock available to fill the gap, creating a more rounded profile. Slow-spreading ridges struggle to keep up, resulting in more tectonic stretching and faulting. But here's what's truly remarkable about the mid-ocean ridge system. It's not ancient. It's not some remnant of the early Earth, frozen in place billions of years ago. It's active. Right now, at this very moment, new ocean floor is being created along its length. Magma is rising from the mantle, erupting onto the seafloor, cooling to form fresh basaltic crust. The ridge is the place where the Earth's tectonic plates are being pushed apart, where new lithosphere is born, where the planet actively renews its surface. In fact, the mid-ocean ridge system is the site of the most volcanic activity on Earth. More than 75% of all the volcanic eruptions on our planet happen underwater along these ridges, not on land, where we can see them and record them and build stories about them, but in the deep sea, hidden from view, silent beneath miles of water. Each year, countless eruptions reshape the seafloor. Lava flows spread across the bottom of the ocean. New volcanic cones rise. Hydrothermal systems flare to life as fresh magma heats the surrounding seawater. And yet we miss almost all of it. We have no cameras there, no sensors, No witnesses except the creatures that live in the darkness. Think about that for a moment. The single most volcanically active feature on our entire planet, a mountain range longer than all the continent's mountain ranges combined, erupting continuously, reshaping the surface of the Earth. And it all happens out of sight, in darkness, in silence, in a world we've barely begun to explore. Less than 1% of the ocean floor has been mapped at high resolution. We have better maps of the surface of Mars than we do of our own seafloor. The mid-ocean ridge, despite being the largest geological feature on Earth, remains largely mysterious. We know it's there. We know roughly where it is. But the details, the small-scale features, the specific locations of active vents and eruption sites, the distribution of life along its length, all of that remains largely unknown. And that's where our story really begins. Because hidden in that darkness, in that crushing pressure, in those rugged volcanic landscapes at the bottom of the sea, there is life. Not just a little life, not just bacteria clinging desperately to existence, but thriving, complex ecosystems, entire communities of organisms that have never seen sunlight, that don't need sunlight, that have evolved to harness energy from the Earth itself. The mid-ocean ridge is home to one of the most alien environments on our planet, and tonight we're going to explore it together. We're going to descend into that darkness and see what's really living there. We're going to witness the impossible made real. We're going to discover how life found a way to exist, not in spite of the extreme conditions, but because of them. So take a deep breath. Feel the weight of the blankets around you, or the cushions beneath you. Feel your body relaxing, settling, preparing for a journey into the deep, because we're about to leave the sunlit world behind and enter a realm where the rules of life are entirely different, where fire and ice exist side by side, where chemistry replaces photosynthesis, where darkness is not the absence of life, but the canvas on which it paints its most remarkable masterpiece, volcanic architecture, the engine beneath. To understand what lives in the mid-ocean ridge darkness, we first need to understand the ridge itself, what it is, how it forms, why it exists, because the life we'll encounter doesn't just live near the ridge, it depends on it. The volcanic and tectonic processes happening miles beneath the seafloor create the conditions that make this life possible. The story begins with plate tectonics, the grand theory that revolutionized geology in the 20th century. The Earth's outer shell, the lithosphere, is not a single unbroken layer. It's divided into several large plates and many smaller ones, all floating on the partially molten asthenosphere beneath. These plates are in constant motion, driven by convection currents in the mantle. Hot material rises from deep within the Earth, cools near the surface, and sinks back down. This slow churning, occurring over millions of years, drives the movement of the tectonic plates. There are three types of plate boundaries where plates interact: convergent boundaries, where plates collide, creating mountains, and subduction zones, transform boundaries, where plates slide past each other horizontally, generating earthquakes, and divergent boundaries, where plates pull apart. The mid-ocean ridge system exists along divergent boundaries. It's where the sea floor is spreading, where plates are moving away from each other, and where new crust is being created to fill the gap. Imagine two massive slabs of rock floating on a sea of partially molten material, being pulled apart by forces so vast they shape continents. As they separate, something has to fill the space between them. That something is magma, molten rock from the Earth's mantle. The process works like this. As the tectonic plates pull apart, pressure on the mantle material beneath decreases. This is called decompression. And when hot rock that's already close to its melting point suddenly experiences less pressure, it begins to melt. Not because it's getting hotter, but because melting point and pressure are intimately connected. Lower the pressure, and solid rock can transition to liquid. This is decompression melting, and it's the primary mechanism that generates magma at mid-ocean ridges. The newly formed magma is less dense than the solid rock around it, so it rises. It percolates upward through the mantle, collecting in magma chambers beneath the ridge axis. These chambers can be several kilometers wide and extend deep into the crust. They're not permanent structures filled with liquid rock like underground lakes. Instead, they're regions where magma exists as a mush, a mixture of crystals and liquid, constantly being replenished from below and constantly feeding eruptions above. When conditions are right, the magma erupts onto the seafloor. It emerges through fissures and cracks along the ridge axis, flowing out as lava. But this isn't the explosive, ash-filled eruption we see on land. Underwater, the immense pressure of the overlying water prevents explosive activity. Instead, the lava oozes out, often forming strange pillow-like structures as the outer surface rapidly cools and solidifies, while the interior remains molten. These pillow lavas are the characteristic volcanic rock of mid-ocean ridges, frozen in shapes that look like giant stacks of pillows or elongated tubes. The lava that forms at mid-ocean ridges has a specific composition. It's called MORB, which stands for Mid-Ocean Ridge Basalt. Basalt is a dark, fine-grained volcanic rock rich in iron and magnesium. MORB is tholeiitic basalt, meaning it's low in incompatible elements like potassium and has a particular chemical signature that distinguishes it from other types of basalt. When scientists find MORB on land, pushed up by tectonic forces, they know they're looking at ancient ocean floor. The rate at which this process happens varies dramatically along the ridge system. As we mentioned earlier, some ridges spread slowly, others quickly. The East Pacific Rise, for example, is one of the fastest spreading ridges on Earth, with plates separating at rates up to 15 centimeters per year. That might not sound like much, but in geological terms, it's remarkably fast. Over 1 million years, that's 150 kilometers of new seafloor. In just 20 million years, enough time for significant evolutionary changes, but a blink of an eye, geologically, that's 3,000 kilometers of new ocean floor, roughly the distance from New York to Los Angeles. At slow-spreading ridges like the Mid-Atlantic Ridge, the rate might be only 2 centimeters per year. Over 1 million years, that's 20 kilometers. Still significant, but the slower rate means less magma is available, leading to more faulting and a more rugged topography. The structure of the oceanic crust created at mid-ocean ridges is layered. At the very top is the pillow basalt layer, the solidified lava flows. Below that is a sheeted dike complex, vertical sheets of frozen magma that once fed the eruptions above. Deeper still is the gabbro layer, coarse-grained igneous rock that cooled slowly within the magma chamber. And beneath all of that is the upper mantle, the source of the magma. This entire package, crust and uppermost mantle, is called oceanic lithosphere, and it's constantly being created at the ridge and slowly moving away as new material forms. As the newly created crust moves away from the ridge axis, it cools and contracts. The seafloor gradually subsides, sinking deeper as it ages. This is why the ocean floor has the characteristic shape it does, highest at the ridge crest and sloping down into deeper abyssal plains on either side. The oldest oceanic crust, found far from the ridges near the edges of continents, is cold, dense, and deep. The youngest crust, right at the ridge axis, is hot, buoyant, and relatively shallow. But the volcanic processes at mid-ocean ridges don't just create rock, they also create heat, tremendous amounts of heat. Magma rising from the mantle brings Earth's internal temperature to the surface, and when that heat interacts with seawater, something extraordinary happens, something that changes the entire character of the mid-ocean ridge from a geological feature into a biological oasis. That heat drives hydrothermal circulation. Seawater seeps down through cracks and fissures in the newly formed crust. It penetrates deep, sometimes several kilometers down, until it encounters the hot rock surrounding the magma chamber. There, the water is heated to extreme temperatures, anywhere from 300 to 400 degrees Celsius or more. That's far above the boiling point of water at the surface, but the immense pressure at depth prevents boiling. Instead, the water becomes superheated, a strange, dense fluid that's almost supercritical. As the water heats up, it becomes chemically reactive. It begins to dissolve minerals from the surrounding rock, sulfur compounds, metals like iron, copper, zinc, manganese. Chemical species that normally don't dissolve readily in water become mobilized in this extreme environment. The hot water also becomes more buoyant as its density decreases. It rises, driven upward by its own heat, traveling back toward the seafloor through channels and fractures. When this superheated, mineral-rich fluid finally reaches the seafloor and erupts into the cold ocean water, something dramatic happens. The temperature difference is extreme. The vent fluid might be 400 degrees Celsius. The surrounding seawater is typically around 2 to 4 degrees Celsius. When they mix, the dissolved minerals precipitate out of solution almost instantly. Metal sulfides, primarily iron sulfide, crystallize and form dark, smoke-like plumes that billow upward into the water column. These are the famous black smokers, the iconic hydrothermal vents that have captured the imagination of scientists and the public alike. But not all vents are black smokers. Some emit cooler fluids, around 200 to 300 degrees Celsius, that are rich in different minerals like barium, calcium, and silicon. These form white or grey plumes, giving rise to white smokers. Other vents are even cooler, with diffuse flows of warm water seeping through cracks in the seafloor, creating temperature gradients without dramatic plumes. And there are alkaline vents, where chemical reactions between seawater and specific rock types produce fluids with high pH and temperatures around 40 to 90 degrees Celsius. Each type of vent creates a unique chemical environment, and each supports different communities of life. The architecture of a vent system can be complex and beautiful in its own alien way. As the hot fluids rise and mix with seawater, minerals precipitate and begin to build structures. At black smokers, iron and other metal sulfides rapidly deposit, forming chimneys. These can grow surprisingly quickly, sometimes several meters in just a few years. They start as small mounds, then develop into towering spires, some reaching tens of meters high. The chimneys are porous, with the vent fluid flowing through channels in their interior and seeping out from sides and top. As the chimney grows, older parts may become inactive, while new structures form, creating complex edifices that look like strange underwater cities. The walls of these chimneys are hot on the inside, in direct contact with the vent fluid, and cold on the outside, bathed in frigid seawater. This creates a sharp temperature gradient across just a few centimeters of rock, and in that gradient, in that narrow zone where extreme heat meets extreme cold, life finds a way. But we're getting ahead of ourselves. Before we meet the life, we need to spend a little more time understanding the stage on which it performs. Because the volcanic and hydrothermal systems of the mid-ocean ridge don't just create heat and chemicals. They create conditions so extreme, so hostile to life as we normally understand it, that the very existence of organisms there seems impossible. And yet, life doesn't just exist, it flourishes. It builds entire ecosystems from scratch, without a single ray of sunlight, in complete and total darkness. Birth of the seafloor, where Earth renews itself. There's something profoundly beautiful about the mid-ocean ridge when you think about it not as a static feature, but as a process, as the place where the Earth actively makes itself new. Every year, approximately 20 cubic kilometers of new oceanic crust is created along the global ridge system. That's rock that didn't exist before. Lava that rises from the depths, cools, solidifies, and becomes part of the ocean floor. In a very real sense, the ridge is where the planet grows. This process, seafloor spreading, is the mechanism that drives plate tectonics. As new crust forms at the ridge and spreads away, it pushes the ocean floor outward. The continents, embedded in their plates, are carried along. This is how the Atlantic Ocean has grown wider over the past 200 million years, how Africa and South America separated from a single supercontinent, how the face of the Earth continually reshapes itself. The youngest rocks on Earth's surface are found right at the ridge axis. They might be only days or hours old, still warm from their formation, move away from the ridge, and the rocks get progressively older. A few kilometers from the axis, they might be thousands of years old. 100 kilometers away, millions of years old. At the edges of ocean basins, where old seafloor approaches trenches and prepares to be subducted back into the mantle, the rocks can be nearly 200 million years old. Old in human terms, but young compared to the Earth itself, which is 4.5 billion years old. Continental rocks can be billions of years old, ancient survivors that have endured eons. But oceanic crust is constantly recycled, created at ridges, and destroyed at subduction zones in a grand conveyor belt that takes roughly 200 million years to complete a cycle. The implications of this are staggering. The ocean floor you see on a map today is not the same ocean floor that existed when dinosaurs walked the Earth. It's not even the same ocean floor that existed when early mammals were just beginning to diversify. The seafloor is new, fresh, constantly being replaced, and the mid-ocean ridge is the factory where this replacement happens. But the ridge doesn't just create rock, it shapes ocean chemistry. The hydrothermal circulation at mid-ocean ridges is a massive ion exchange system. Hot water flows through the crust, dissolves certain elements, and deposits others. The net effect is that elements are continuously being added to the ocean and removed from it through this process. Iron, sulfur, manganese, silicon, helium-3, all of these are introduced to seawater at vents. Some remain dissolved, others precipitate and settle back to the seafloor. Still others are taken up by biological processes. Scientists estimate that the entire volume of Earth's oceans circulates through mid-ocean ridge hydrothermal systems approximately every 10 million years. That means that over geological timescales, every drop of seawater in the ocean has passed through a vent system at least once. The chemistry of the ocean, the salinity, the trace element composition, even the pH, are all influenced by these deep-sea interactions between hot rock and cold water. There's also the matter of heat. Tremendous amounts of heat are released at mid-ocean ridges. The magma, the hot rock, the superheated fluids all contribute to warming the ocean, albeit very slowly and on a global scale. Some estimates suggest that the cooling of newly formed oceanic crust and the associated hydrothermal circulation account for about 30% of the Earth's total heat loss. That's significant. It means that the mid-ocean ridge system plays a fundamental role not just in creating seafloor, but in regulating the planet's thermal budget. And then there are the earthquakes. Lots and lots of earthquakes. The mid-ocean ridge is a seismically active place. As plates pull apart, rock fractures, faults slip, magma forcing its way upward cracks the overlying crust. Most of these earthquakes are small, imperceptible, except to sensitive seismographs, but they happen constantly, a steady drumbeat of seismic activity that marks the ridge as a zone of active deformation. Occasionally, larger quakes occur. They're not the devastating magnitude 8 or 9 monsters that happen at subduction zones, but they can still be significant. And for the creatures living on the seafloor, these quakes can be life-altering events. Sections of the ridge can collapse, hydrothermal chimneys can topple, vents can shut off abruptly as their plumbing gets disrupted, or new vents can open, sudden bursts of scalding water in places where none existed before. The volcanic eruptions themselves are both destructive and creative. A new lava flow can bury existing communities, covering them in fresh basalt, but it can also create new habitat, new surfaces for organisms to colonize. The heat from a fresh eruption can kickstart new hydrothermal systems, bringing nutrients and chemical energy to areas that were previously dormant. There's a dance here, a constant interplay between creation and destruction. The ridge doesn't offer stability. It doesn't provide a safe, unchanging environment. Instead, it's a place of flux, where the only constant is change. And the life that exists there has evolved to cope with that, to take advantage of the fleeting nature of its home, to reproduce quickly, to disperse widely, to colonize new sites before the old ones disappear. Some vent fields can last for decades, even centuries. They become long-term oases in the deep, with established communities and complex food webs. But others are ephemeral, flaring to life for just a few years before tectonic shifts or changes in magma supply shut them down. It's estimated that the average lifespan of a vent field is somewhere between a few decades and a few centuries, though some have certainly persisted much longer. For the organisms living there, this creates a biogeographical challenge. How do you maintain a population when your habitat keeps disappearing? How do you find new vents when they're scattered across thousands of kilometers of ocean floor? The answer, as we'll see, involves remarkable adaptations. Larvae that can drift in the deep ocean currents for weeks or months, traveling vast distances, chemical sensing abilities that allow organisms to detect the plumes of new vents from kilometers away, life histories that emphasize rapid growth and early reproduction, getting as much done as possible before the inevitable end. But again, we're jumping ahead. We need to descend deeper, both physically and conceptually, into the environment itself, because understanding the ridge is only the first step. To truly grasp what lives there, we need to experience the conditions those organisms face every single moment of their lives. The pressure, the temperature extremes, and most importantly, the darkness. The absolute, complete, and utter darkness that defines the deep sea. The darkness below, a world without light. Close your eyes for a moment, not to sleep, not yet, but to experience something. Sit in complete darkness. If you're in a room with any light at all, even the faint glow of a phone or a nightlight, imagine it gone. Imagine that every photon, every particle of light has been extinguished. That's a hard thing to do, actually. Our world is full of light. Even at night, there are stars, the moon, the distant glow of cities. We've never experienced true, absolute darkness. But the mid-ocean ridge exists in that darkness. Not the darkness of a cloudy night, not the darkness of a cave where you've walked far from the entrance, but total, primordial darkness. The kind of darkness that has persisted since the formation of the Earth. The kind of darkness that exists not because lights have been turned off, but because light has never reached there. Let's follow a photon, a particle of light, on its journey from the sun to the deep ocean. It leaves the sun traveling at 300,000 kilometers per second, the ultimate speed limit of the universe. 8 minutes later, it reaches Earth. It passes through the atmosphere, scattering and filtering but largely surviving. It strikes the ocean surface, and here, its journey takes a dramatic turn. Even in the clearest ocean water, light doesn't penetrate far. The water molecules themselves absorb and scatter light. So do dissolved organic materials, microscopic particles, plankton. Different wavelengths of light are absorbed at different rates. Red light, with its longer wavelength, is absorbed first, within the top 10 meters or so. This is why underwater photographs taken without artificial light have that blue-green cast. The warm colors are simply gone, absorbed by the water. By about 200 meters depth, even in the clearest tropical waters, 99% of surface light has been absorbed. This is called the photic zone, the layer of the ocean where there's enough light for photosynthesis. Below this, in what's called the dysphotic or twilight zone, some light remains, but it's faint. Too faint for plants to use, but still detectable by organisms with sensitive eyes. By 600 to 1,000 meters depth, even this faint light has disappeared. This is the aphotic zone, where photosynthesis is impossible, where the human eye would see absolutely nothing, and we're still not even halfway to the average depth of the mid-ocean ridge. At 2,600 meters, the typical depth of the ridge crest, there has been no sunlight for billions of years. None. Not a single photon from the sun has reached this place in longer than complex life has existed on Earth. The darkness is not temporary. It's not seasonal. It's absolute and eternal. This has profound implications for life. On the surface, nearly every ecosystem is built on photosynthesis. Plants and algae and cyanobacteria use sunlight to convert carbon dioxide and water into sugars and oxygen. They're the primary producers, the base of the food web. Everything else, all the herbivores eating plants, all the predators eating herbivores, all the decomposers breaking down dead material, they all ultimately depend on the energy captured from sunlight. Take away the sun, and the entire system collapses. Or so we thought. The deep sea, away from hydrothermal vents, is actually a desert. Nutrients and organic matter do sink down from the surface. A constant rain of dead plankton and fecal pellets and marine snow drifting down through the water column. This provides some food for deep-sea organisms, but it's scarce. The biomass, the total weight of living organisms per unit area in the deep abyss, is extremely low. Life exists, but it's sparse, spread thin, surviving on scraps that fall from the world above. But at hydrothermal vents, the biomass is comparable to that of tropical rainforests. Despite the darkness, despite the depth, despite the isolation from the sun's energy, the concentration of life at vents is so high that when they were first discovered, scientists were shocked. It didn't make sense. Where was the energy coming from? The answer, as we'll see in detail soon, is chemosynthesis. But before we get there, let's sit with the darkness a little longer, because darkness isn't just the absence of light, it's a selective pressure. It shapes evolution in specific ways. Many deep-sea fish have enormous eyes, maximizing their ability to detect the faintest bioluminescence from other organisms. Others have lost their eyes entirely, evolving instead to rely on other senses like smell, vibration detection, or electrical field sensing. In the absolute darkness, sight is useless. Other senses become more important. At hydrothermal vents, most organisms have reduced or absent eyes. The giant tube worms have no eyes at all. The vent crabs have eyes, but they're not particularly good. Some vent shrimp have evolved a different kind of photoreceptor, sensitive not to visible light, but to the faint infrared glow emitted by the hot vent fluids. It's not vision in the way we understand it, but it allows them to sense the temperature gradient and avoid getting too close to the scalding water. The darkness also affects behavior. Without day-night cycles, there are no circadian rhythms based on light. Organisms must use other cues, perhaps temperature fluctuations or chemical signals, to regulate their activity. Reproduction timing, which in many surface organisms is linked to day length, must be governed by different mechanisms. And then there's the simple psychological impact of imagining it. When you try to picture life at a hydrothermal vent, you have to set aside all your visual references. There is no sunlight dappling through water, no colors, except those provided by artificial lights on research submersibles, no shadows, no dawn or dusk, just blackness, eternal blackness. And in that blackness, life not only survives but thrives in ways that rewrite our understanding of biology. But darkness is just one aspect of the extreme conditions at the mid-ocean ridge. There's also the pressure. At sea level, atmospheric pressure is about 1 bar, or 14.7 pounds per square inch. It's what we're adapted to, what feels normal. For every 10 meters of depth in the ocean, the pressure increases by approximately 1 atmosphere. So at 10 meters depth, the pressure is 2 atmospheres. At 100 meters, 11 atmospheres. At 1,000 meters, 101 atmospheres. At the typical depth of the mid-ocean ridge, 2,600 meters, the pressure is about 260 atmospheres. That's 260 times the pressure at the surface. Or, put another way, about 3,800 pounds per square inch. If you extended your hand at that depth without protection, the pressure would be equivalent to having a large car sitting on every square inch of your skin. This pressure would instantly crush anything with an air-filled cavity. Lungs would collapse, eardrums would rupture, the air spaces in the human body would be compressed to nothing. This is why deep-sea organisms don't have air bladders like surface fish do. They can't afford air spaces. Instead, their bodies are essentially incompressible, filled with water and tissues that don't compress. But pressure doesn't just crush, it also affects chemistry and biochemistry. Proteins, the workhorses of cellular function, can be deformed by high pressure. The shape of a protein determines its function, and pressure can alter that shape. Deep-sea organisms have evolved proteins that maintain their structure and function under pressure, sometimes through specific amino acid substitutions that make the protein more pressure-tolerant. Cell membranes, which need to be fluid to function properly, become more rigid under pressure. To compensate, deep-sea organisms often have membranes with a higher proportion of unsaturated fatty acids, which remain fluid even under high pressure. It's a subtle adjustment, but it's absolutely necessary for life at depth. And then there's temperature. We've talked about the hot fluids at vents, but the ambient water temperature in the deep ocean is frigid, around 2 to 4 degrees Celsius, just above freezing. That's cold enough to slow most biochemical reactions to a crawl. Surface organisms would simply stop functioning. Their enzymes would be too sluggish. Their metabolism would shut down. But deep-sea organisms have cold-adapted enzymes that work efficiently at low temperatures. Their cellular machinery is tuned to the cold, just as ours is tuned to the warmth of the surface. So at hydrothermal vents, organisms face a paradox. The ambient water is nearly freezing, but just centimeters away, the vent fluids can be 400 degrees Celsius. The temperature gradient is extreme. An organism might have its feet in scalding water and its head in near-freezing water. This creates enormous physiological challenges. Some organisms position themselves precisely in the gradient, taking advantage of the mixing zone where warm and cold water meet, creating a narrow range of tolerable temperatures. Others, particularly the microbes growing directly on the chimneys, have evolved remarkable heat tolerance, surviving and thriving at temperatures that would denature proteins in most organisms. Add all of this together: the crushing pressure, the near-freezing cold alternating with extreme heat, the total darkness, the isolation from the surface, the instability of the habitat, and you have conditions so extreme, so hostile, that life should be impossible. And yet, it's not. Life has found a way. In fact, life has found multiple ways, evolving a stunning diversity of strategies to not just survive, but flourish in this impossible place. The key, the absolutely critical factor that makes it all possible, is chemistry. Not the chemistry of sunlight and photosynthesis, but the chemistry of the Earth itself. The chemistry of minerals, of dissolved gases, of electron transfers in the darkness. This is where our story takes its most remarkable turn. This is where we discover that life doesn't need the sun as much as we thought. As long as there's energy somewhere, some source of chemical disequilibrium that can be exploited, life can figure out how to use it. Welcome to the world of chemosynthesis. Welcome to life, powered not by starlight, but by earthlight. Chemosynthesis, life without sunlight. Let's start with a simple truth. Life requires energy. Every organism, from the smallest bacterium to the largest whale, needs a constant supply of energy to maintain its structure, to grow, to reproduce. Without energy, the molecules of life fall apart. Order becomes disorder. Life becomes death. On the surface, that energy comes primarily from the sun. Photosynthesis, performed by plants, algae, and some bacteria, captures light energy and uses it to build sugar molecules from carbon dioxide and water. The equation is elegant and essential. 6 molecules of carbon dioxide, 6 molecules of water, and sunlight yield 1 molecule of glucose and 6 molecules of oxygen. The glucose stores the energy from sunlight in its chemical bonds. That sugar then powers the plant's metabolism, and when animals eat the plants, it powers them too. The oxygen released as a byproduct is what we breathe. The entire surface biosphere, with very few exceptions, runs on this process. But photosynthesis cannot happen without light, and at the mid-ocean ridge, there is no light. So how does life obtain energy? The answer was not immediately obvious. When hydrothermal vents were first discovered in 1977 during an expedition to the Galapagos Rift, scientists were exploring the seafloor in the deep-sea submersible Alvin. They expected to find a barren landscape, perhaps a few scavengers eking out an existence on scraps from the surface. What they found instead shocked them. Clustered around fissures in the seafloor, bathed in shimmering warm water, were dense communities of organisms unlike anything seen before. There were clams the size of dinner plates, clusters of white crabs, shimmering clouds of shrimp, and most striking of all, tube worms. Tall, white tubes topped with brilliant red plumes, swaying in the current. These tube worms, later named Riftia pachyptila, grew in dense groves, like a bizarre underwater forest. Some were over 2 meters tall, 6 feet or more. The biomass around these vents was staggering. In an environment that should have been a desert, here was an oasis. But where was the food coming from? There were no plants, no algae. The nearest photosynthetic organisms were kilometers above. At the surface, how could so much life exist here? The mystery deepened when scientists collected samples of the vent fauna and examined them. The tube worms had no mouth, no digestive system, no anus. They couldn't eat. They had a blood-filled body, a tough tube, and that red plume. That was it. How were they obtaining nutrients? A young graduate student named Colleen Kavanagh had a hypothesis. She had been thinking about bacteria. In certain environments, bacteria don't use photosynthesis. Instead, they use chemical reactions to obtain energy, a process that had been observed in sulfur springs and other extreme environments. These bacteria, called chemosynthetic or chemoautotrophic bacteria, oxidize reduced chemical compounds like hydrogen sulfide or methane, using the energy released to build organic molecules. Kavanagh proposed that similar bacteria might be living in symbiosis with the tube worms. The worms would provide a home for the bacteria, and the bacteria would provide food for the worms. It seemed far-fetched, but when tissue from the tube worms was examined closely, there they were, billions of bacteria packed into a specialized organ called the trophosome, living inside the worms' bodies. The pieces started to fit together. The hydrothermal vent fluids were rich in hydrogen sulfide, a compound that's highly toxic to most organisms. But these bacteria could use it. They oxidized the hydrogen sulfide, combining it with oxygen to form sulfate, and captured the energy released in that reaction. They used that chemical energy to fix carbon dioxide from the seawater into organic compounds, sugars, and other molecules. Then they shared those nutrients with their host worm. In return, the worm absorbed hydrogen sulfide and oxygen from the water, using its plume, and transported them to the trophosome where the bacteria lived. It was a perfect mutualism, a partnership where both organisms benefited. This process, using chemical energy instead of light energy to build organic molecules, is called chemosynthesis. The fundamental equation is similar to photosynthesis in its outcome. Carbon dioxide is converted into organic matter, but the energy source is completely different. For sulfur-oxidizing bacteria, the reaction involves hydrogen sulfide, oxygen, and carbon dioxide, yielding organic carbon and sulfate. The energy from oxidizing the sulfide fuels the fixation of carbon dioxide. Instead of food made from sunlight, it's food made from Earth's chemistry. This was revolutionary. It meant that photosynthesis, while dominant, was not the only game in town. Ecosystems could exist. Entire complex food webs could be sustained without any connection to the sun whatsoever. As long as there was a source of chemical energy, life could build upon it. And the mid-ocean ridge had chemical energy in abundance. The hot vent fluids weren't just hydrogen sulfide. They also contained methane, hydrogen gas, ferrous iron, manganese, and ammonia. All of these are reduced compounds that can be oxidized for energy. Different bacteria specialized in different chemical reactions. Some used sulfide, some used methane, some used iron or manganese, others used hydrogen gas. The diversity of chemical strategies was astonishing. This meant that the base of the food web at hydrothermal vents wasn't plants, it was bacteria and archaea. Chemosynthetic microorganisms, invisible to the naked eye, formed the foundation on which everything else was built. They were the primary producers, converting inorganic chemicals into organic matter, and they did it in complete darkness, using energy from the earth rather than the sun. Some of these microbes lived freely, floating in the vent fluids or attached to rock surfaces, forming thick white or yellow bacterial mats. Others formed symbiotic relationships with larger organisms. The tube worms were just one example. Giant clams housed bacteria in their gills. Vent mussels did the same. Even some vent shrimp carried bacteria on their backs or in their gill chambers. These partnerships allowed the larger animals to tap into the chemosynthetic energy source indirectly, benefiting from the bacteria's ability to harness chemical energy. The efficiency of chemosynthesis varies depending on the chemical reaction. Oxidizing hydrogen sulfide yields a moderate amount of energy. Oxidizing methane yields more, but none of these reactions is as energetically favorable as photosynthesis under optimal conditions. A photosynthetic organism in bright sunlight can fix carbon much faster than a chemosynthetic bacterium oxidizing sulfide. So why bother with chemosynthesis at all? Because chemosynthesis doesn't depend on sunlight, and sunlight doesn't penetrate to the deep sea. At hydrothermal vents, there's no photosynthetic option. It's chemosynthesis or nothing. And while chemosynthesis may be less efficient than photosynthesis per unit energy input, there's one huge advantage. The chemical energy at vents is continuously supplied by the volcanic and tectonic processes beneath. As long as the Earth remains geologically active, as long as magma rises and heats seawater, the vents will keep pumping out reduced chemicals. In a sense, vent ecosystems are powered by the heat of the Earth's interior, by the same primordial energy that has kept our planet's core molten for billions of years. There's another fascinating aspect to chemosynthesis. It doesn't just happen at hydrothermal vents. It's found in many other environments where reduced chemicals are available. Sulfur springs on land, mud volcanoes, sewage systems. Believe it or not, waterlogged soils where oxygen is depleted. Even in the sediments of the deep ocean floor, far from vents, chemosynthetic bacteria eke out an existence by slowly oxidizing buried organic matter or methane seeping from below. Chemosynthesis may even be ancient, older than photosynthesis. Early Earth had a very different atmosphere, lacking oxygen and with abundant volcanic gases. Some scientists think that the first living organisms might have been chemosynthetic, using chemical reactions rather than light to obtain energy. If so, life may have begun in a place much like a hydrothermal vent, in the darkness of the deep sea or in hot springs on land, long before photosynthesis evolved and transformed the atmosphere. This connection between modern vent ecosystems and the origin of life is tantalizing. It suggests that studying the mid-ocean ridge isn't just about understanding a unique ecosystem, it's about understanding the very roots of biology itself, the fundamental ways that life can harness energy and build complexity. And it raises another question. If life can exist at hydrothermal vents on Earth, could similar life exist elsewhere in the solar system? Europa, one of Jupiter's moons, is covered in ice, but beneath that ice is a global ocean, and there's evidence that Europa might have hydrothermal vents on its seafloor, driven by tidal heating from Jupiter's immense gravity. If so, could there be chemosynthetic microorganisms there, living in the darkness beneath kilometers of ice, powered by the chemistry of their alien world? Enceladus, a moon of Saturn, also has a subsurface ocean, and geysers of water erupt from cracks in its icy crust. Those geysers contain organic molecules and chemical disequilibrium that could support life. Perhaps in the oceans of Enceladus, right now, there are microbes performing chemosynthesis, building ecosystems in the dark. These aren't just idle speculations. They're serious questions being investigated by astrobiologists. The discovery of chemosynthesis at hydrothermal vents fundamentally changed our understanding of where life can exist. It expanded the habitable zone, the range of conditions under which life seems possible. It taught us that life doesn't need sunlight as much as we once thought. It needs energy and chemistry, and those exist in many places we never expected. But we're getting ahead of ourselves again. Before we venture to alien oceans, let's stay focused on our own planet's mid-ocean ridge, because the chemosynthetic microbes we've been discussing, while foundational, are just the beginning. They're the base of the food web. But standing on that base is an entire ecosystem of bizarre and wonderful organisms, each adapted in its own way to life in the volcanic darkness. And among those organisms are some of the strangest extremophiles Earth has ever produced. Microbes that thrive in conditions so extreme they challenge our very definition of what life can tolerate. It's time to meet the extremophiles. The extremophiles, life at the edge. The term extremophile literally means lover of extremes. It refers to organisms, usually microbes, that thrive in conditions we consider hostile: high temperatures, extreme cold, intense pressure, acidic or alkaline pH, high salinity, high radiation. Environments that would kill most organisms are home sweet home for extremophiles. Hydrothermal vents are a haven for these remarkable microorganisms. In fact, vents might host the highest concentration and diversity of extremophiles anywhere on Earth. Let's meet some of them. First, the thermophiles and hyperthermophiles. These are organisms that love heat. Thermophiles thrive at temperatures between about 45 and 80 degrees Celsius. Hyperthermophiles take it further, growing optimally at temperatures above 80 degrees Celsius, with some species capable of surviving and reproducing at temperatures above 100 degrees Celsius, well above the boiling point of water at sea level. The current record holder is Methanopyrus candleri, a species of archaea that can grow at 122 degrees Celsius. At such temperatures, proteins in most organisms would denature and fall apart. DNA would be damaged. Membranes would lose their structure. But these organisms have evolved special adaptations. Their proteins contain extra bonds and modifications that stabilize their three-dimensional structure at high temperatures. Their DNA is often wound more tightly and protected by special proteins. Their membranes have unique lipids that remain intact even when hot. These aren't just minor tweaks. They're fundamental redesigns of cellular machinery, optimized for heat. Methanopyrus candleri is particularly interesting because it's not just heat-tolerant, it's also a methanogen. It produces methane as a metabolic byproduct, using hydrogen gas and carbon dioxide in an energy-yielding reaction. It lives on the walls of black smoker chimneys, right where the scalding vent fluids exit. The environment there is not only hot but also rich in dissolved minerals, high in pressure, and completely dark. Yet Methanopyrus candleri thrives, part of a microbial community that forms the base of the vent ecosystem. Another group of extremophiles found at vents are the acidophiles and alkaliphiles, organisms that live at extreme pH. The vent fluids themselves can be acidic, with pH values as low as 2 or 3, or alkaline, with pH values up to 11, depending on the type of vent and the rock through which the fluid has circulated. These extreme pH values affect protein structure and cell function, yet certain bacteria and archaea have evolved to cope. They maintain a neutral pH inside their cells while living in an external environment that's highly acidic or alkaline, using specialized pumps and membrane proteins to regulate ion balance. Then there are the piezophiles, organisms adapted to high pressure. At the depths where hydrothermal vents are found, the pressure is immense, and it affects biochemical reactions in subtle ways. Piezophiles have proteins and membranes that function optimally under high pressure. Some species actually require high pressure to grow. They can't survive at atmospheric pressure. If you bring them to the surface, they die. Not from lack of pressure exactly, but because their biochemistry is so finely tuned to deep-sea conditions that it fails to function properly without it. There are also halophiles, organisms that thrive in high salinity. While seawater itself isn't extremely salty compared to, say, the Dead Sea, the mixing of vent fluids with seawater can create localized areas of varying salinity. Some vent microbes are adapted to these fluctuations, maintaining cellular function across a range of salt concentrations. And then there are the polyextremophiles, organisms that tolerate multiple extreme conditions simultaneously. At hydrothermal vents, this is the norm rather than the exception. A typical vent microbe might be a thermophile, a piezophile, and resistant to high concentrations of toxic metals, all at the same time. It might also be a chemolithotroph, deriving energy from inorganic chemical reactions. These organisms are extremophiles in multiple dimensions, pushing the boundaries of what we consider survivable. One particularly fascinating group are the sulfur bacteria and archaea. Hydrogen sulfide is the dominant reduced chemical at many vents, and entire communities of microbes have evolved to exploit it. Some, like the sulfur oxidizing bacteria, oxidize sulfide to elemental sulfur or sulfate, capturing energy in the process. Others, the sulfate-reducing bacteria, do the reverse, using sulfate as an electron acceptor and producing sulfide as a byproduct. This creates a sulfur cycle at vents, with different microbes performing different steps, collectively recycling sulfur through various oxidation states. One genus in particular, Thiomicrospira, is extremely abundant at vents. These are small, motile bacteria that swim through the vent fluids, oxidizing sulfide and fixing carbon dioxide. They form dense populations in the mixing zones where vent water meets seawater, creating turbid clouds of microbial biomass. Other common genera include Thiothrix and Begiatoa, both of which form filamentous structures and are capable of nitrogen fixation, turning atmospheric nitrogen into forms that other organisms can use. Methane is another important chemical at some vents, particularly at cooler sites or where specific rock types are present. Methanotrophs, bacteria that oxidize methane, are abundant in these environments. They use oxygen to oxidize methane to carbon dioxide, capturing energy in the process. This is ecologically significant because methane is a potent greenhouse gas, and methanotrophs help prevent large amounts of vent-sourced methane from escaping into the ocean and atmosphere. There's also a group of bacteria called iron oxidizers. They use ferrous iron, the dissolved form of iron that's abundant in vent fluids, and oxidize it to ferric iron, forming rusty-colored deposits. The energy yield from iron oxidation is relatively low, so these bacteria have to process a lot of iron to make a living, but they're remarkably successful at vents, forming conspicuous orange and brown stains on rocks and chimneys. What's truly astonishing about these extremophiles is not just that they survive extreme conditions, but that they've adapted their entire biology to exploit those conditions. The heat, the pressure, the toxic chemicals aren't obstacles to be overcome, they're resources to be used. The very things that make vents hostile to surface life are what make them habitable for extremophiles. These microbes also play a crucial ecological role beyond being primary producers. They're the nutrient cyclers, breaking down and transforming chemicals, making elements like nitrogen, sulfur, and iron available in forms that other organisms can use. Without them, the larger vent animals couldn't exist. The tube worms, the clams, the shrimp, they all ultimately depend on the metabolic activities of these tiny extremophiles, and there's a practical dimension to studying these organisms. Extremophiles have already yielded important biotechnological applications. Enzymes from thermophiles, called thermostable enzymes, are used in molecular biology. Taq polymerase, the enzyme used in PCR, the polymerase chain reaction that amplifies DNA, comes from a thermophilic bacterium originally discovered in a hot spring. Other enzymes from extremophiles are used in industrial processes, biofuel production, and pharmaceuticals. The metabolic pathways of extremophiles also inspire new approaches to sustainability. Could we design industrial processes that mimic the chemistry of vent bacteria, converting waste products into useful compounds? Could extremophile metabolism inform the development of carbon capture technologies, ways to remove carbon dioxide from the atmosphere using biological or bio-inspired systems? These are active areas of research. There's also the evolutionary perspective. Extremophiles show us that life is more flexible, more adaptable than we ever imagined. The range of conditions under which organisms can function is vastly broader than what we experience in our everyday lives. This suggests that life as a phenomenon is robust, capable of persisting in environments we might write off as uninhabitable. And it means that when we look for life elsewhere in the universe, we shouldn't limit our search to Earth-like conditions. We should look in lava tubes on Mars, under the ice of Europa, in the ammonia-rich clouds of gas giants, anywhere there's liquid water, chemical energy, and a source of raw materials, because if life can thrive at hydrothermal vents on Earth, in darkness, under crushing pressure, surrounded by toxic chemicals and scalding water, then it can probably find a way to exist in all sorts of unexpected places. But let's return to the mid-ocean ridge. We've talked about the microbial base of the ecosystem, the extremophiles that harness chemical energy. But an ecosystem is more than just bacteria. There's a whole community of larger organisms, macrofauna, that depend on those microbes. And some of those larger organisms are among the most bizarre and captivating creatures ever discovered. It's time to meet them. Giant tube worms and symbiosis, a partnership forged in darkness. Picture a garden, not a garden of flowers, but a garden of worms. Tall, pale tubes rising from the seafloor, swaying gently in the current. From the top of each tube emerges a plume, brilliant red, almost blood-colored, billowing like a flower or a feather. This is the forest of giant tube worms, and it's one of the most striking sights at hydrothermal vents. The giant tube worm, Riftia pachyptila, is an icon of deep-sea biology. When it was first discovered at the Galapagos Rift in 1977, it redefined what scientists thought was possible. These worms can grow up to 3 meters long, almost 10 feet, making them one of the largest soft-bodied invertebrates in the ocean. But size isn't what makes them remarkable, it's how they live. An adult Riftia has no mouth, no gut, no anus. It cannot eat. It has no way to ingest food in the traditional sense. For an animal, this seems impossible. Animals eat. That's how they get nutrients. But Riftia has evolved an entirely different strategy. It doesn't eat. Instead, it farms. It farms bacteria. Inside the body of the worm, occupying a large portion of its internal volume, is a specialized organ called the trophosome. This organ is not found in any other type of animal. It's a dense mass of tissue filled, absolutely packed, with billions of symbiotic bacteria. These bacteria are sulfur oxidizers, similar to the free-living chemosynthetic microbes we discussed earlier. They use hydrogen, sulfide, oxygen, and carbon dioxide to produce organic compounds through chemosynthesis. The bacteria get a safe, protected place to live, and in return, they provide the worm with all the nutrients it needs. But how do the worm and the bacteria exchange materials? The worm has a remarkable system. Its plume, that brilliant red structure at the top of the tube, is packed with blood vessels. The red color comes from hemoglobin, the same oxygen-carrying molecule found in our blood. But Riftia's hemoglobin is special. It can bind not only oxygen but also hydrogen sulfide, both at the same time. This is extraordinary because hydrogen sulfide is toxic to most organisms. It interferes with cellular respiration. Yet Riftia has evolved hemoglobin that can carry this poison safely through its bloodstream without it causing harm. The worm extends its plume into the water, absorbing oxygen and hydrogen sulfide from the vent environment. It also takes up carbon dioxide. All three of these substances are transported by the blood to the trophosome, where the bacteria are waiting. The bacteria use the oxygen and sulfide to generate energy through oxidation, and they use the carbon dioxide to build sugars and other organic molecules. These nutrients diffuse from the bacteria into the worm's tissues, nourishing the worm. The bacteria, in turn, receive a continuous supply of the raw materials they need for chemosynthesis, delivered by the worm's circulatory system. It's an elegant solution. The worm acts as a mediator, bringing together substances that exist separately in the environment: oxygen in the ambient seawater, sulfide in the vent fluids, and delivering them to the bacteria. The bacteria do the metabolic heavy lifting, converting inorganic chemicals into organic food. Both partners benefit, a classic mutualism. But the story gets even more interesting. How does the worm acquire its bacterial symbionts in the first place? For a long time, This was a mystery. Adult worms are completely dependent on their bacteria. Without them, the worms would starve. But the bacteria aren't passed from parent to offspring. Riftia eggs don't contain bacteria. The larvae hatch without symbionts. They're aposymbiotic, lacking the partnership that defines adult worms. It was only recently that scientists figured out how the infection happens. The larvae drift as plankton in the deep water for a time. When they settle onto the seafloor near a vent, they undergo metamorphosis. During this process, they develop a temporary mouth and gut. Bacteria from the surrounding environment enter through the skin, not through the mouth as originally thought. This was a surprising discovery. The bacteria essentially infect the larva, passing through the skin and colonizing the internal tissues that will become the trophosome. Once the bacteria are established, the larva's mouth and gut degenerate and disappear. The juvenile worm seals itself inside its tube, extends its plume, and begins its symbiotic adult life. This raises fascinating questions. How do the larvae find the right bacteria? Vent environments are full of microbes, but only specific species can form the symbiosis. The worm must have some mechanism for selecting or encouraging the right bacteria while excluding others. The details of this recognition process are still being studied. Riftia pachyptila grows remarkably fast, among the fastest growing marine invertebrates known. Under favorable conditions, a worm can grow over 80 centimeters, more than 30 inches, in a single year. This rapid growth is fueled by the efficiency of the symbiosis. The worm gets a constant supply of nutrients from its internal bacteria, and it doesn't expend energy on foraging or digestion. All its resources can go toward growth and reproduction. But this lifestyle comes with risks. Riftia is sessile, meaning it's fixed in place. It lives attached to the seafloor, unable to move. If the vent it's living near shuts off, if the flow of hydrogen sulfide stops, the worm has a problem. Without sulfide, the bacteria can't perform chemosynthesis. Without chemosynthesis, the worm doesn't get fed. And because the worm has no mouth, it can't switch to feeding on something else. It's completely dependent on the vent. If the vent dies, the worm colony dies with it. This makes vent ecosystems ephemeral from the worm's perspective. Vents are geologically short-lived. They can shut off due to volcanic or tectonic activity. The Earth shifts, magma chambers cool, fluid pathways get blocked. When that happens, entire vent fields can go quiet, and the tube worm forests vanish. This is why Riftia has evolved a life history that emphasizes fast growth and early reproduction. Get big, reproduce, send your larvae out into the water column, and hope they find a new vent somewhere else. It's a bet hedging strategy in an uncertain world. The symbiosis between Riftia and its bacteria is so intimate that it's sometimes hard to say where one organism ends and the other begins. The bacteria are not just living inside the worm, they're integrated into its biology. They're essentially an organ, like a liver or a kidney, performing a function the worm can't do on its own. This kind of symbiosis, where partners are tightly coupled and interdependent, is called obligate symbiosis. Neither partner can survive without the other, and Riftia isn't alone. Many vent organisms form symbioses with chemosynthetic bacteria. Giant clams, like Calyptogena magnifica, house bacteria in their gills. Bathymodiolus mussels do the same. In some species, the mussels have two different types of bacteria, one that oxidizes sulfide and another that oxidizes methane, giving the mussel flexibility in what chemical environments it can exploit. There are even some vent snails that carry bacteria on their shells, grazing them like tiny underwater ranchers. These symbioses are not limited to hydrothermal vents. Similar partnerships exist at cold seeps, places on the seafloor where methane or hydrogen sulfide seep out from the sediment. There are tube worms at seeps too, though different species from Riftia. 1. Lamellobrachia lumesi is notable for its longevity. While Riftia grows fast and lives for a few decades at most, Lamellobrachia grows slowly and can live for over 250 years, possibly as long as 300 years, making it one of the longest-lived non-colonial invertebrates on Earth. The discovery of these symbioses fundamentally changed biology. It showed that ecosystems could be powered by partnerships between macroorganisms and microbes, with the microbes harnessing chemical energy and the larger organisms providing structure and delivery systems. It blurred the line between individual and community, between organism and ecosystem. In a sense, a tube worm isn't just an animal. It's a walking, or rather, sessile, chemosynthetic factory, a collaboration between animal and bacteria that together exploit an energy source neither could use alone. And it's beautiful in its own strange way. The tube worm forests, with their crimson plumes waving in the current, are some of the most visually striking ecosystems on Earth. When submersible lights illuminate them, they glow against the black basalt and the dark water, a splash of color in the abyss. They're a reminder that life, given the opportunity, will find a way to be both functional and, in its own alien way, aesthetically compelling. But Riftia is just one member of a much larger community. The tube worm forests are surrounded by a diverse assemblage of other organisms, each with its own role, its own adaptations. Let's explore that community more broadly and meet some of the other residents of the vent ecosystem. The vent community, an ecosystem in the abyss. Step back from the tube worms and take in the full scene at a hydrothermal vent. What you'd see, if you were in a submersible with its lights piercing the darkness, is a bustling, crowded community. Not the sparse, quiet expanse of the abyssal seafloor, but a vibrant oasis teeming with life. Clustered around the black smoker chimneys, coating the rocks with white or orange or yellow films, are dense mats of bacteria. These free-living chemosynthetic microbes form thick biofilms, sometimes centimeters deep, and they're so abundant that they change the texture and appearance of the seafloor. The mats sway slightly in the current, a ghostly carpet that marks the zones of warm water mixing with cold. On and around the bacterial mats, you'll find vent snails, small gastropods that graze on the bacteria like tiny underwater cows. Some species have shells covered in iron sulfide scales, a strange adaptation that might provide protection or structural support in the mineral-rich vent environment. The most famous of these is the scaly foot snail, Chrysomalon squamiferum, which has a shell reinforced with layers of iron sulfide, giving it a metallic appearance. Nearby are fields of giant clams, half buried in sediment or nestled in cracks between rocks. Like the tube worms, these clams host chemosynthetic bacteria in their gills and rely on the symbiosis for nutrition. They can be quite large, with shells reaching 20 or 30 centimeters across. Their siphons extend into the water, drawing in oxygen and carbon dioxide for their bacterial partners while filtering out nutrients. Mussels are also common, often forming dense beds that carpet the rocks. These are not the mussels you'd find at a seafood market. These are vent mussels, species like Bathymodiolus thermophilus, adapted to life at high temperatures and under pressure. Their shells are often stained orange or brown from the iron-rich vent fluids, and they attach to the substrate using tough threads called byssal threads. Inside their gills, billions of bacteria perform chemosynthesis, just like in the clams and tube worms. Then there are the crustaceans. Vent crabs, like Bythagria thermidron, scuttle across the rocks on long, spindly legs. They're omnivores and scavengers, feeding on bacterial mats, bits of dead worms, whatever they can find. They're also predators, and they'll attack the tube worms, nipping at their exposed plumes with their claws. The worms can retract into their tubes for protection, but if a crab manages to tear off part of a plume, the worm is wounded and vulnerable. There are also the famous vent shrimp, which can be found in staggering numbers. At some vents, particularly in the Atlantic, swarms of shrimp blanket the chimneys, so dense that they obscure the rock beneath. These are often species like Rimicaris exoculata, blind shrimp that lack functional eyes but have light-sensitive organs on their backs. These organs can detect the faint infrared glow from the hot vent fluids, allowing the shrimp to navigate the temperature gradient and avoid getting cooked. The shrimp carry bacteria on their bodies, either in their gill chambers or on their backs, and they're essentially mobile bacterial farms, constantly harvesting and reseeding their microbial partners. There's even a species of crab that's become iconic, the yeti crab, Kiwa hirsuta, and related species. These crabs have long, hairy claws covered in filaments that look like fur but are actually covered in bacteria. The crabs hold their claws out into the vent flow, cultivating the bacteria, and then periodically scrape the bacteria off and eat them. They're actively farming microbes, tending their bacterial gardens like underwater ranchers. Fish are less common at vents than invertebrates, but they're present. Vent fish, like species in the genus Thermaces, can be found hovering near the warm water, taking advantage of the abundant food. They feed on the invertebrates, the shrimp, the crabs, the snails. They're not vent specialists in the way tube worms are. They can live away from vents, but they're attracted to the high biomass. There are also eels, including the remarkable Dysomena rugosa, which gathers in large numbers at some vent fields. One site, nicknamed Eel City, near American Samoa, was found to have thousands of eels living in burrows and crevices, feeding on the vent shrimp and other invertebrates. Eels are unusual at vents. Most vent communities are dominated by invertebrates, so finding a vertebrate-dominated site was a surprise. Even octopuses visit vents. Deep-sea octopuses, species that normally live in the cold abyss, have been observed at vent sites, likely attracted by the abundance of prey. They're not vent specialists, but opportunists, exploiting the food-rich environment when they encounter it. The vent community also includes worms other than the iconic tube worms. There are polychaete worms, many species of them, living in crevices, burrowing in sediment, or building tubes of their own. One particularly heat-tolerant species is Alvinella pompeiana, sometimes called the Pompeii worm. This worm lives directly on the chimney walls of black smokers, in some of the hottest habitats on Earth. The tail end of the worm can be exposed to temperatures exceeding 80 degrees Celsius, while the head end, which pokes out into the colder water, is much cooler. The worm tolerates a temperature gradient across its body that would be lethal to most organisms. It, too, hosts symbiotic bacteria, which cover its body in a fuzzy mat, and these bacteria likely play a role in detoxifying the extreme environment. Limpets, anemones, barnacles, various types of worms all contribute to the diversity. In total, over 500 species have been described from hydrothermal vent ecosystems, and that number continues to grow as more vents are explored. Many of these species are endemic to vents, found nowhere else on Earth. They've evolved specifically to exploit the unique conditions there. The food web at vents is complex. At the base are the chemosynthetic microbes, both free-living and symbiotic. These are the primary producers, building organic matter from inorganic chemicals. The next level includes grazers, animals like snails, and some shrimp that feed directly on bacterial mats. Then there are filter feeders, like the mussels and clams, which take in bacteria and organic particles from the water. Above them are the predators, crabs, fish, octopuses, that feed on the grazers and filter feeders. And at the top are scavengers and decomposers, organisms that feed on dead material and recycle nutrients back into the system. But it's not a simple linear chain. There are loops and connections everywhere. Crabs eat bacterial mats, but they also scavenge dead worms. Tube worms rely on bacteria, but they also filter organic particles from the water as a supplementary food source. Shrimp farm bacteria on their bodies but also graze on free-living mats. The ecosystem is a web, not a ladder, with energy and nutrients flowing in multiple directions. One of the most striking things about vent ecosystems is their isolation. Vent fields can be separated by hundreds or even thousands of kilometers of seafloor. Each vent is like an island, an oasis surrounded by the biological desert of the abyss. This raises a question. How do organisms disperse from one vent to another? How do populations remain connected? The answer lies in the larval stage. Most vent organisms have a dispersal phase, usually as free-swimming larvae that drift in the water column. These larvae can be carried by deep-sea currents, traveling vast distances. Some may drift for weeks or months before settling. This dispersal is critical for maintaining genetic connectivity between vent populations and for colonizing new vents when they open. But larval dispersal is risky. The larvae must survive the journey through the deep ocean, where food is scarce and predators lurk. They must find a new vent before their energy reserves run out. And they must be lucky enough to land in a place where a vent is active. If they settle too far from a vent, where there's no sulfide or methane, they'll starve. If they land at a vent that's about to shut off, they'll die. It's a high-stakes lottery, and most larvae don't make it. But enough do that vent populations persist, and new vents, when they form, are quickly colonized. Scientists study larval dispersal using genetic tools, comparing the DNA of organisms from different vent sites to see how connected they are. They found that some species are widely distributed, with gene flow across entire ocean basins. Others are more localized, with distinct populations at each vent field. The patterns of connectivity help us understand how vent ecosystems are linked across the global mid-ocean ridge system. There's also an interesting biogeographic puzzle. Vent fauna on one side of the planet are often quite different from those on the other side. The vents in the Pacific have different species than the vents in the Atlantic, which have different species than those in the Indian Ocean. This suggests that vent ecosystems have evolved independently in different ocean basins, with some barriers to dispersal preventing organisms from spreading everywhere. The details of this biogeography are still being worked out, but it's clear that the history and geography of vent ecosystems is complex, shaped by ocean circulation, the positions of tectonic plates, and the evolutionary history of the organisms themselves. What's truly remarkable is that all of this diversity, all of this complexity, exists in an environment that's completely devoid of sunlight. The vent ecosystem is a testament to the power of chemistry as an energy source. It shows that photosynthesis, while dominant, is not the only foundation for life. Given the right conditions, life can build elaborate, multi-level communities based entirely on geothermal energy and chemosynthesis. And it makes you wonder, if vents can support such richness in the deep sea, what other energy sources might life be exploiting that we haven't discovered yet? Are there ecosystems powered by radioactive decay, organisms living in deep crustal rocks feeding off the energy released by natural radioactivity? Are there communities sustained by chemical reactions in subglacial lakes beneath Antarctic ice? The discovery of vent ecosystems opened our eyes to the possibilities. It taught us to look beyond the obvious, to consider that life's solutions can be far more creative than we imagined. But let's not forget the physical structures that make all of this possible. The chimneys, the vents, the mineral deposits. These are not just inert geological features, they're part of the ecosystem, shaping it, defining it, providing the substrate and the chemical gradients that life depends on. It's time to look more closely at these structures, to understand how they form and what role they play in the life of the vent community. Mineral chimneys and chemical gardens. When you picture a hydrothermal vent, the image that likely comes to mind is a black smoker, a tall chimney belching dark smoke into the water. This iconic structure is more than just scenery. It's a dynamic, growing, evolving feature that's intimately tied to both geology and biology. A black smoker chimney forms through precipitation. When the superheated vent fluid, laden with dissolved minerals, hits the cold seawater, the temperature drop causes those minerals to fall out of solution. They crystallize almost instantly, forming tiny particles. The most common mineral is iron sulfide, which gives the plume its black color. Other sulfides, like copper, zinc, and lead, also precipitate, along with various other compounds depending on the fluid chemistry. These particles don't just drift away. Many settle onto the seafloor or onto existing structures, accumulating over time. As more and more fluid passes through, more minerals deposit, and slowly, incrementally, a chimney grows. The process is self-reinforcing. Once a small mound or structure exists, it channels the flow of the vent fluid, concentrating deposition in certain areas. The chimney grows upward and outward, building itself taller and more complex. The structure of a chimney is not solid. It's porous, riddled with channels and passages through which the hot fluid flows. Think of it as a plumbing system made of precipitated minerals. The fluid rises through the interior, seeps out from various points on the surface, and deposits more material as it exits. The walls of the chimney are layered, with different minerals crystallizing at different temperatures. The innermost layers, in contact with the hottest fluid, might contain minerals that form only at high temperatures. The outer layers, where the fluid has cooled and mixed with seawater, contain different minerals. Some chimneys grow remarkably fast. In a matter of years, a chimney can rise from nothing to several meters high. The tallest known chimney, discovered at a vent field on the Juan de Fuca Ridge, was over 15 meters tall before it toppled. That's about 50 feet. A 5-story building made entirely of precipitated minerals. But chimneys are not stable forever. They're fragile structures, and they can collapse. The minerals are brittle, and the internal plumbing can get clogged or redirected. Tectonic earthquakes can shake them down, or they simply grow too tall and heavy, their foundations unable to support the weight, and they fall. When a chimney collapses, it leaves behind a pile of debris, sulfide-rich rock that becomes substrate for a new generation of organisms. Old, collapsed chimneys are often colonized by worms, mussels, and other fauna, their porous structure providing habitat. The mineral deposits at vents are economically significant. The sulfide minerals that form chimneys contain high concentrations of metals: copper, zinc, gold, silver. These are the same metals that humans mine on land, and some of the richest ore deposits in the world. Ancient massive sulfide deposits formed at hydrothermal vents millions or billions of years ago. Those deposits were later uplifted and exposed by tectonic processes, making them accessible. This has led to interest in deep-sea mining. Could we extract valuable metals from active or inactive vent sites? It's technically feasible, but it raises serious environmental concerns. Vent ecosystems are fragile, and mining would destroy them. There are also questions about the long-term impacts on ocean chemistry and biology. For now, most scientists and environmentalists advocate for extreme caution and comprehensive research before any mining takes place. But chimneys are not the only mineral structures at vents. There are also flanges, flat, overhanging structures that form when mineral-rich fluids pool beneath a layer of rock and precipitate upward, creating a kind of inverted chimney. These can be large, several meters across, and the underside of a flange can host unique communities of organisms living in the warm, mineral-rich water trapped beneath. There are also diffuse flow areas, places where warm water seeps through sediment or porous rock rather than erupting from a focused vent. These areas don't have dramatic chimneys, but they're biologically important. The temperature is lower, more moderate, and the chemical environment is different, which attracts different organisms. Some species prefer the cooler diffuse flow over the extreme heat of black smokers. And then there are the white smokers and alkaline vents, which we've mentioned before. These produce different minerals: barium sulfate, calcium carbonate, silica, resulting in white or light-colored deposits. The Lost City vent field, located off the Mid-Atlantic Ridge, is an example of an alkaline vent system. It's powered not by magma but by a chemical reaction called serpentinization, where seawater reacts with certain rock types, producing hydrogen, gas, methane, and heat. The chimneys at Lost City are made of carbonate and are much more delicate and towering than typical sulfide chimneys. With some structures reaching over 60 meters high, the vent fluids are alkaline, warm rather than scalding, and support a different community of organisms. What all these structures have in common is that they create gradients, temperature gradients, from scalding to freezing across centimeters, chemical gradients, with high concentrations of specific compounds in some zones and low in others. These gradients are critical for life. They provide a range of microhabitats, allowing different organisms with different tolerances to coexist in a small area. On one part of a chimney, where it's extremely hot, only hyperthermophilic archaea can survive. A few centimeters away, where the water has cooled, thermophilic bacteria thrive. Further out, where temperatures are moderate, larger organisms like tube worms and mussels settle. And beyond that, in the cooler zones, crabs, fish, and other mobile fauna patrol. The chimneys also provide structure. In the otherwise relatively flat expanse of the abyssal seafloor, a vent chimney is a landmark, a high-rise in the desert. It creates three-dimensional habitat, surfaces for attachment, crevices for hiding, channels for fluid flow. Without the chimneys, the vent ecosystem would look very different, much flatter and less diverse. In a way, the chimneys are alive, not biologically, but in the sense that they're dynamic, growing, changing, interacting with their environment. They're shaped by both geological and biological processes. Geology creates them, biology colonizes them, and together they form a system where the boundary between living and non-living blurs. There's a poetic quality to that. The Earth itself, through volcanic heat and mineral-rich water, builds structures that become homes for life, and life, in turn, influences those structures, stabilizing them with bacterial mats, breaking them down, redistributing the minerals. It's a conversation between the planet and its inhabitants, played out in the darkness of the deep ocean, far from the influence of the sun. Implications and mysteries, the questions that remain. We've journeyed from the surface, through the darkness, to the glowing vents at the bottom of the sea. We've met the extremophiles, the tube worms, the crabs and shrimp, and we've seen how an entire ecosystem can function without sunlight, powered instead by the Earth's own heat and chemistry. But every answer in science brings new questions, and the study of mid-ocean ridge ecosystems is no exception. One of the most profound questions is about the origin of life itself. Could life have begun at a hydrothermal vent? The conditions at vents, chemical energy, mineral surfaces for reactions, a continuous supply of nutrients, resemble hypothetical early Earth environments. The early Earth's atmosphere was very different from today, lacking oxygen but rich in carbon dioxide, methane, and other gases. The oceans were likely full of dissolved iron and other metals. Volcanic activity was more intense. In many ways, the early Earth was a planet-sized vent field. Some scientists propose that life began at undersea vents, where chemical reactions could provide energy, and where the mixing of different chemical environments could drive the formation of complex organic molecules. Others favor hot springs on land, or even shallow ponds. The debate is ongoing, but the existence of chemosynthetic ecosystems at modern vents lends support to the idea that life could have originated in similar settings. If it happened once, billions of years ago, it might have happened at a vent. There's also the question of extremophile diversity. We've identified hundreds of species at vents, but how many more are there? The mid-ocean ridge system is vast, and we've explored only a tiny fraction of it. Every time scientists visit a new vent field, they discover new species. It's estimated that there could be tens of thousands of microbial species associated with vents, most of them unknown to science. Even among the larger animals, there's likely hidden diversity, cryptic species that look similar but are genetically distinct. And what about the microbes living inside the rocks? There's growing evidence that microbial life exists deep in the oceanic crust, far below the seafloor, in cracks and pores in the rock. These subseafloor biospheres might be enormous, with biomass rivaling that of the surface ocean. How do these subsurface ecosystems interact with vent ecosystems? Do organisms from vents colonize the deep crust, or vice versa? This is a frontier of research. Another mystery is how vent ecosystems will respond to changes in ocean conditions. Climate change is altering ocean temperature, chemistry, and circulation patterns. Will this affect vent ecosystems? They're not directly dependent on surface conditions, but they're not completely isolated either. Changes in ocean circulation could affect larval dispersal, making it harder for organisms to reach new vents. Ocean acidification, caused by increasing atmospheric carbon dioxide dissolving in seawater, could alter the chemistry of vent fluids or the ability of organisms to build shells. We don't yet know. There's also the question of human impact. As we've mentioned, there's interest in deep-sea mining. If mining occurs at or near vent fields, it could destroy ecosystems that took decades to establish. And because vents are patchy and isolated, loss of a single vent field could mean extinction of species found nowhere else. Regulations are being developed, but the science is still catching up to the technology. We need to understand these ecosystems much better before we start exploiting them. And then there's the astrobiology angle. The discovery of chemosynthesis at hydrothermal vents has revolutionized the search for life beyond Earth. We're no longer limiting our search to planets in the habitable zone, the narrow range of distances from a star where liquid water can exist on a surface. Now we're looking at icy moons with subsurface oceans, places like Europa and Enceladus, where hydrothermal activity might provide energy for life even in the absence of sunlight. Future missions to these moons aim to sample their plumes or drill through the ice to reach their oceans. If we find life there, it might be chemosynthetic, living in darkness, powered by chemical energy from the moon's interior. The parallels to Earth's mid-ocean ridge ecosystems would be undeniable, suggesting that the principles of life, the ways energy can be harnessed and ecosystems built, are universal. There's also the question of communication. How do vent organisms find each other in the darkness? How do larvae locate new vents? Chemical signals are likely involved, detecting the plumes of hydrogen sulfide or other vent-specific compounds from a distance. But the details are poorly understood. Some organisms might use sound, or vibrations, or even electrical fields, though these are speculative. And what about consciousness and cognition? We tend to think of deep-sea organisms as simple, driven purely by instinct, but some of them have complex behaviors. Octopuses, for example, are highly intelligent. Crabs learn and adapt. Even shrimp, navigating the fine gradients between deadly heat and nutrient-rich warmth, display a kind of problem-solving. What is it like to be a vent organism? We can't know, but it's worth contemplating. Finally, there's the mystery of resilience. Vent ecosystems are ephemeral, constantly under threat from volcanic eruptions, tectonic shifts, and the eventual shutdown of vents. And yet they persist, populations recover, new vents are colonized. The global system of vent ecosystems, despite its patchiness, has existed for millions of years. How do these organisms maintain such resilience? What genetic or life history traits allow them to bounce back from near-extinction events? Understanding this could teach us about resilience in other ecosystems, even those on land, as they face rapid environmental change. Closing reflections, wonders in the dark, and so we return from the abyssal depths, from the glowing chimneys and the forests of tube worms, from the realm of extremophiles and symbiotic partnerships, we ascend back through the darkness, through the crushing pressure, back toward the world we know. But you're changed now, aren't you? Not physically, but in understanding. You've seen what exists in a place most people will never visit, a place that was unknown to humanity until just a few decades ago. You've witnessed life thriving not in spite of extreme conditions, but because of them. You've seen ecosystems powered not by the sun, but by the restless heat of the Earth's interior. The mid-ocean ridge is many things. It's the longest mountain range on the planet. It's a volcanic factory where new seafloor is born. It's a chemical reactor where minerals are dissolved and precipitated. It's a biological hotspot where extremophiles rewrite the rules of what life can tolerate. And it's a reminder that our world still holds secrets, vast tracts of territory unexplored, ecosystems undiscovered, species unnamed. There's a humility in that. We've sent probes to the edge of the solar system, captured images of galaxies billions of light years away, and yet we've barely scratched the surface of our own ocean. Less than 1% of the deep sea has been explored. The mid-ocean ridge, despite being a planetary-scale feature, remains largely unknown. Each expedition brings new discoveries, new species, new mysteries, and there's a beauty in that darkness. Not a visual beauty, since there's no light to see by, but a conceptual beauty. The elegance of chemosynthesis, the partnership between worm and bacterium, the resilience of life in the face of chaos. These are beautiful ideas, beautiful systems, as worthy of awe as any sunset or starry sky. When you lie in bed tonight, or whenever you choose to sleep, you can rest with the knowledge that beneath the waves, miles down, in total darkness, life continues. Chimneys grow. Bacteria convert sulfide to sulfate. Tube worms sway in the current. Crabs scuttle across the rocks. The earth breathes. And life responds, endlessly creative, endlessly adaptable. You might feel small when you think about it, insignificant in the face of such vastness and strangeness. But I'd invite you to feel something else. Feel connected, because you are made of the same atoms as those vent organisms. Your body runs on chemical reactions not so different, in principle, from the ones powering chemosynthesis. Your cells harness energy, build molecules, maintain order against entropy, just like the bacteria in a tube worm's trophosome. Life is one phenomenon, expressed in a stunning diversity of forms. From the sunlit forests to the darkest abyss, from the photosynthetic to the chemosynthetic, from the familiar to the alien, it's all connected. It's all part of the same grand experiment, the same ancient lineage, stretching back billions of years to the first cells that figured out how to capture energy and use it to persist. And perhaps that's the deepest lesson of the mid-ocean ridge. Life doesn't need the sun. It doesn't need light or warmth or any of the comforts we take for granted. All it needs is energy, some chemical disequilibrium to exploit, and time. Given those, it will find a way. It will adapt, evolve, diversify, thrive. So as you drift towards sleep, let your mind wander back to those chimneys, those worms, those glowing plumes of mineral-rich water. Let the darkness be not frightening but comforting, a reminder that even in the absence of light, there is life, there is beauty, there is wonder. Let the pressure of the deep ocean metaphorically lift the pressure of your day. Let the stillness of the abyss quiet the noise in your mind. The mid-ocean ridge will be there tomorrow, and the next day, and 1,000 years from now, slowly spreading, constantly erupting, eternally hosting its strange and wonderful communities. It doesn't need us to survive, but we, perhaps, need it. We need the reminder that our world is vast and deep and full of surprises. We need the humility of knowing how much we don't know. We need the inspiration that comes from discovering that life is more resourceful, more resilient, more extraordinary than we ever imagined. Thank you for descending with me into the darkness. Thank you for sitting with the extremophiles, for marveling at the tube worms, for contemplating the chemistry of life without sunlight. I hope you found it as fascinating as I do. I hope it sparked something in you, a curiosity, a sense of wonder, a deeper appreciation for the hidden worlds beneath the waves. And now, rest. Let the rhythm of the ocean, the slow spread of the seafloor, the patient glow of the vents, lull you towards sleep. Let the knowledge that life is everywhere, even in the places we consider uninhabitable, give you peace. Because if life can thrive in the crushing, freezing, lightless abyss, then surely there's hope for all of us, wherever we are, whatever challenges we face. The mid-ocean ridge is out there, right now, beneath miles of water, in complete darkness. And it's alive, wonderfully, impossibly alive. And so are you. Rest well.